Here we look at simple graphs that are bipartite. So a simple graph G is called bipartite if the set of vertices, so that's what we called capital V, the set of vertices, can be partitioned into two disjoint sets, such that every edge in the graph connects a vertex in V1 to a vertex in V2. So all edges are accounted for, and they're going from a set V1 to V2, so you're able to connect over. So we don't want connections within this set itself, so we don't want to have these two connected like so. Let's look at an example. Here, this is a simple graph, and we will show that it's bipartite. And one way to show this is if you can, so it will be bipartite if and only if you can assign one of two colors to each vertex so that no two adjacent vertices have the same color. So again, you're only choosing two colors, and let's see if we can make this bipartite. So again, bipartite meaning you can break it up into the two sets that are disjoint. What is the adjacency table for this? So I can look at the adjacency table, putting down the vertex A, vertex B, C, and D. What is A adjacent to? Well, A shares an edge with B and C. So A is neighbors or adjacent to B and C. B is adjacent to A. C is adjacent to A and D, neighbors with A and D. They share an edge. And D only shares an edge with C. So that's the adjacency table. And what we can do is we can pick on two colors. So I'm just going to use orange. And if I use orange for A, for example, I'm going to assign A orange. So A needs to be orange. And you can look at the adjacency table, just fill in all the oranges here. This one's a quick one, so I know that maybe I'll choose the green now. So if A is orange, then its adjacent vertices, which happen to be B and C here, they both need to be opposite. So they both need to be green. So B needs to be green, C needs to be green. So I'm just going to fill that out here. And then that just leaves me with my other color that I had before, which was orange, for D. So D needs to be orange, D needs to be orange. So as I look at this, I can see that, so it's easy to see on an adjacency table, that if I have a vertex here and the vertex is orange, then you do have opposite colors for its adjacent vertices, for its neighbors. So it does have orange, and then to the right all green, or on this one, B is green, to the right all orange, C is green, to the right all orange. So they're opposite in colors here. So you're able to separate this into two distinct sets, disjoint that is. And what would those sets be? Well, it would be A and D, the color that you assigned orange, and the other color would be B and C, and it connects. So A is connecting over to B and C, and what else do we have? So A is connecting to B and C, and what's D connecting? D is connecting over to C. Okay, so that's how we get the separate vertices, V1 and V2, so that all of the edges are connecting from V1 and to V2, but not within the sets themselves. So this is an example that is not bipartite. Again, we can choose two colors, and if I choose my color orange for A, for example, so I'm going to let A be orange, then I would just fill this out and say, okay, A needs to be orange everywhere that I have an A. Hopefully I filled out my adjacency table correctly. A is neighbors with B, neighbors with E, F, okay, etc. Then what does that mean for the adjacent vertices? Well, they need to be a different color, so I'm going to use green here. Now, what's adjacent to A? B needs to be green, E needs to be green, and F. So I need to have B, I need to have E, and I need to have F. So I would just, fill that out again. So B, all the B's, then I said all the E's and all the F's. Now, do we have a problem? We can check. Okay, already I know that I can stop, so this is a problem here. If I look to the left and to the right, this one's fine. This has it separated, orange and then green. This one is not separated right away. I see that I have a mix over here on the right side. I have A is the orange and E and F are green here. I also have a mix here with the A and those other colors. So this is not going to be bipartite. Now you could look and think about what would a subgraph of this be so that I do get this to be bipartite. So that's another reason we look at subgraphs. We might want to remove edges here so that we do have a bipartite graph. So let's look at a different example that is bipartite again. So if I looked at this and pick on my colors again, we just work it out the same way. We can pick A as one color. So if we're choosing A to always be the first color, for example, I would just fill this out. And then all of its adjacent vertices need to be the second color. So you only have two colors here. What's adjacent? Well, C is E, F, and G. So we have C, E, F, and G. And I can fill that out, C, E, F, and G. So C, E, F, and G. And then if I look at what the other color, or what's left, I'm using orange here, that means that I need, for E, is adjacent to B, and D, so those both need to be orange. So I'm going to fill those out with orange, the B's, and all the D's. And so the adjacency table is a little bit, I think, this one, you know, it's not obvious unless I look at all the lines here. If I look at the graph, it doesn't always go, it depends on how you draw it, you know, it doesn't always go orange and then green, orange and then green, but here I am able to see it separated. I have the separate to the left and to the right for this row, it's separate to the left and to the right. Yeah, the colors are separated. So this is bipartite. And this graph would be separated into one set V1 and V2. So you want to include all the vertices, and the color, for example, orange was A, B, and D. So that would be V1. And then the rest of it, C, E, F, and G, which was our green, would be on the other side. And they would have the connection. I'm not going to draw it, but you know, A goes to C, A goes to E, etc. You know, you would just finish out that they do have the connection of every edge from V1 to V2, but not a connection within the sets themselves. So this is bipartite.